In this video, we will explore the rendering pipeline used by OpenGL ES and Vulkan graphics APIs, and the role that each pipeline stage plays. Before we explore the graphics pipeline in detail, let's do a quick pass over the approach taken. We start with an object built by an artist. These objects are described using a mesh of triangles that define an infinitely thin skin around the outside of an object. These objects are hollow. We are only modeling their outer shape, not what they contain. For each frame of rendering, we animate each vertex in the mesh to place the object correctly sized and oriented in both our virtual environment and on the screen. The GPU will then rasterize the visible triangles, taking the vector form of each triangle and determining which pixels need to be colored in. These pixels are then color shaded and written out into the frame buffer. By repeating this process for every object in the scene, we can incrementally render the whole image that is to be displayed. What does this pipeline look like in terms of processing stages? There are 4 main stage groups involved. The CPU runs the application and the graphics driver. It is responsible for graphics pre-flight, such as animation and physics, uploading the CPU-generated data into the DRAM, and sending the rendering commands to the GPU. The command processing stage is a control stage inside the GPU, responsible for interpreting the requests made by the CPU and coordinating the GPU's data processing stages. The geometry processing stage takes the input meshes designed by the content artists, animates each vertex into the correct location in screen space, generates an additional per-vertex data payload such as per-vertex lighting, and emits a stream of primitives, most commonly triangles, for pixel processing to consume. The pixel processing stage consumes this primitive data, rasterizes it to generate pixel coverage, and executes the fragment coloring operations. To run this process, the CPU must upload different types of data resource. Shader programs for each programmable stage define the processing operations to be performed on each vertex or each fragment. Buffers contain the input vertex data, primitive connectivity data, and other information about the scene such as transformation matrices for each object, or information on each dynamic light source. Textures contain image data, both color and non-color, that can be used by the shader stages as input. They can also be used as frame buffer attachments and store the output of the rendering process. Descriptors are control plane structures that provide supplemental information to the GPU. Each resource needs a descriptor to describe where it is in memory and how it should be accessed. Each rendering command will reference a descriptor which tells the GPU about the configuration of the draw call, and lists all the resources that are needed to complete the operation. When a CPU issues a command to the GPU, the command processor will read the descriptor describing the draw call and use this to parameterize the rest of the pipeline. The geometry processing step will produce a set of vertices and primitives that are visible on screen. Then, the pixel processing stage will color them in and write them out into the frame buffer. In this example, the first instruction tells the GPU to draw the moon, using the descriptor D1. A subsequent instruction, using descriptor D2, draws the Earth, using the same buffer and shaders, but with a different texture. The one stage I've not really talked about is the compute processing stage. This is because the compute processing really exists outside the main rendering pipeline. The other stages form a strict pipeline, with data being handed from one stage to the next until the final output is available for the application. Compute exists outside of this, consuming inputs from main memory and writing outputs back to main memory in the form of modified buffers and textures. This allows compute to be involved at any point in the pipeline, for example, producing procedurally generated meshes stored in a buffer for geometry processing, but in a rather loosely connected way. The geometry processing stage group consists of multiple component pipeline stages. Object space vertices enter the pipeline, are processed by a number of user-defined programmable stages, shown in green, and fixed function stages, shown in blue, getting turned into screen space primitives which are passed on down the pipeline to pixel processing. The vertex shading stage consumes the vertex stream from the application, animating each vertex in the mesh and computing any additional per-vertex data needed in the later pipeline stages. It is a stream processing stage. Every vertex in a draw call executes a unique copy of the vertex shader, has read-only inputs, and runs in isolation, even from other vertices in the same mesh or primitive. The tessellation shading stage is an optional stage which can be used to programmatically subdivide the primitives in a model, allowing for more detailed geometry to be built on the fly. It's actually a 3-stage mini pipeline consisting of 2 shader stages linked by a fixed function tessellator. The first shader stage, the control shader, determines how much subdivision to apply. The tessellator then creates new primitives that have been asked for. Finally, the second shader stage, the evaluation shader, pushes and pulls the tessellated geometry into place. The real power of tessellation is that it is able to alter the silhouette outline of an object, adding detail where there was none in the input model. This is something that cannot be achieved by pseudo-geometry techniques such as normal mapping. However, tessellation is a very expensive technique, which is difficult to use well, so it is rarely used in shipping mobile content. The geometry shading stage is an optional stage which can be used to programmatically create or destroy new primitives, using the stage input primitives as a source of control data to define the geometry shader operation. One common use case has been to produce particle systems on the fly, using the input mesh to define the time step and animation state of the particles that need to be created. In reality, geometry shaders are now a legacy technique. Most of the use cases where geometry shaders can be applied can be more efficiently solved using compute shaders instead. They are rarely used. Primitive assembly takes the vertex stream from the earlier stages of the pipeline and groups the vertices back into the point, line, and triangle primitives that are needed by the later stages in the pipeline. This construction can use implicit assignment, using the vertex ordering to define each primitive, or explicit construction, using a dedicated index buffer to associate vertices with primitives. Explicit construction is more efficient, outside of trivial cases, as it allows for each vertex to be used more effectively. Once we have the primitives in the final coordinate system, we can work out what is potentially visible inside the view volume, and discard those which are not, reducing the amount of work passed on to the pixel processing. Primitives which are outside the view volume can be discarded, as we can guarantee they do not map to a screen pixel. Primitives which are inside the view volume but facing away from the camera, typically the back face of a model, can be killed by the facing test. This top pipeline is the pipeline you will read in the API specifications, but it has one major inefficiency. Calling happens at the end of the pipeline, after we've spent precious energy processing the vertices. Even in well-written content, with perfect application side calling, we expect to throw away around half the vertices, because they are the back face of the visible mesh. Most GPUs therefore reorder the pipeline to pull calling as early as possible. The bottom pipeline shows the behavior of modern Mali GPUs, introduced with Mali G71, the first of the Bifrost architecture designs. In this approach, the vertex shader is split into two pieces by the shader compiler, the first half computing position, the second computing the remaining non-position output attributes. Only the position shader runs before culling. The varying shader is run afterwards, and only runs for vertices that contribute to visible primitives. We'll revisit this technique later in the series, as applications can use good buffer layout to maximize the benefit it gives. It is worth noting that even with this approach, culling happens after some vertex processing has occurred. It is highly recommended that applications use techniques to efficiently cull entirely off-screen draw calls in software, in order to avoid wasting power budget on things that literally have no impact on the final render. The pixel processing pipeline consists of a single shader stage, the fragment shader, with a large amount of fixed function support functionality. Screen space primitives are passed in, and, hopefully, beautifully rendered pixels drop out at the far end. The first stage in pixel processing is rasterization. This takes the ideal vector form of each triangle and compares it against a per-pixel sample mass to determine which parts of the frame buffer get colored in. Commonly, each pixel will generate a single invocation of the fragment shader, but the invocation rate can be higher, using sample rate shading, or lower, using variable rate shading, than 1:1. One important thing to note with rasterization is that the output it generates are 2x2 fragment patches called quads. Quads form the dispatch granularity for fragment shading, the 4 fragments combining to provide the spatial coverage needed to generate the derivatives needed for MIP mapping and anisotropic filtering. Small triangles which only hit a subset of the sample points inside a quad will simply run the fragment shader with idle lanes in the hardware, reducing the shader execution efficiency. In the left-hand diagram, we can see a small triangle which covers 10 pixels, but due to partial coverage of quads, it is consuming 20 pixels worth of the fragment shading capacity. After rasterization, quads are submitted for early Z, depth, and S stencil testing. This allows samples that are occluded by either other objects or stencil masks to be discarded before fragment shading. Killing things at early ZS is relatively inexpensive, so it is recommended that applications aim to use this as much as possible. The fragment shading stage computes a color value for the fragments. What happens here is entirely under the control of the application, but it is important to note that the shader code can determine which optimizations get applied by the other parts of the pixel processing pipeline. For example, programmatically modifying the GL frag depth in the shader will prevent early ZS from being used, and force the fragment to fall back to late ZS testing. More on this later in the series. The late ZS test happens after fragment shading, and handles all of the depth and stencil test and update that could not be processed early. Killing things after fragment shading is expensive, so applications should aim to minimize the amount of late ZS testing happening. The blend stage is a fixed function stage which handles blending any transparent pixels into the frame buffer, based on the application's requested blend function. As with geometry processing, this top pipeline is the pipeline you will find if you read the API specification. It consists of two common sources of inefficiency. Firstly, early ZS testing is very dependent on the application sending in geometry in the correct order. To benefit from the specified depth test, the application must pass in geometry in a front-to-back render order, starting closest to the camera and working further away. An application processing geometry back to front will get no benefit from the depth test. Each new primitive will be closer to the camera than its predecessors, and therefore visible. Late ZS happens after we have completed all of the shading. As with the geometry pipeline, we want to pull this as early as possible, so we do not spend cycles shading things that are ultimately discarded. To work around the early ZS geometry ordering problem, most modern hardware has some form of hidden surface removal that is capable of removing occluded fragments even if the occluder is later in the primitive stream. While aiming to render front to back is still recommended, this does provide a means to catch geometry in the wrong order and remove most of the associated cost. Late ZS test and update is commonly integrated as a shader trigger roll operation, allowing it to be invoked as soon as any prerequisite shader computation has occurred. This minimizes the amount of redundant processing for fragments that are killed by late testing. One concept that is tightly woven into pipelines is that of parallel processing. The analogy of a physical pipe where the work is pushed into one end, everything inside it moves along, before eventually dropping out the far end sometime later, is an accurate portrayal of the desirable behavior here. We can imagine our pipeline as consisting of three macro stages: the application building a draw call on the CPU, the geometry processing on the GPU, the pixel processing on the GPU. These stages will run in sequence as work moves down the pipeline, so to keep all the processing units busy, we need to have multiple operations in flight concurrently. Here, we can see that once we reach a steady state, all of our processing units are busy, which will give the peak performance of this design. Keeping the GPU in this state of overlap is one of the most important objectives when optimizing rendering workloads. Note that the overlap in this diagram is purely illustrative. We'll come back to the actual overlap patterns for different hardware a little later in the series. If applications are not careful, they can break the pipeline, causing either a complete pipeline drain or the serialization of one or more stages. The loss of parallelization will cause a corresponding drop in rendering efficiency. For OpenGL ES, the API exposes a synchronous behavior model, even though the underlying processing in modern hardware is definitely asynchronous, so the driver has to work hard to maintain the programmer's model illusion of synchronicity. Some API calls will enforce the synchronous behavior, such as the GL finish in this example, forcing the pipeline to drain. Vulkan is designed for modern hardware, so exposes an asynchronous programming model. This requires the application to define which operations can run in parallel by expressing dependencies between the data producers and consumers. Making these dependencies too conservative will result in a serialized execution of one or more stages, and another drop in efficiency. When optimizing a pipelined processing architecture, which is running with good overlap, it is important to know that the slowest pipeline stage is the one that will set the performance. In the example in the diagram, we can see an application which is taking longer to produce a draw call on the CPU than they take to process on the GPU. To make this application run faster, we must look at the CPU side optimizations to reduce that draw construction cost. The next video in this series will explore how the rendering pipeline translates into GPU hardware. Visit the ARM developer website for more information about ARM Mali graphics solutions.